Welcome to the lecture on queuing theory, module 3. In this module, we will develop and study two queuing models, model 1 general, which is MM1 infinitive FCFS, and model 2, which is MM1 N FCFS. In the first model, we consider the arrival rate and service rate, which is dependent on the size of the system, whereas the capacity of the system is unlimited. Whereas, in the second model, the arrival rate and service rates are assumed to be constant, that is independent of the size of the system, but the capacity of the system is limited. We will consider examples to show how the results of this model can be applied to solve some queuing problems. Let us now discuss model 1 general, which is MM1 infinitive FCFS. The assumptions of this model are same as model 1, which as discussed in the previous model. The only difference is that the arrival rate and service rate are assumed to be here dependent on the size of the system. Let us suppose that the arrival rate and service rate depend on n, the size of the system. We take arrival rate lambda equal to lambda n and service rate mu equal to mu n. Then, by the same arguments as in model 1, we get P n t plus delta t equal to P n t into 1 minus lambda n into delta t minus order of delta t into 1 minus mu n into delta t minus order of delta t plus P n t into lambda n delta t plus order of delta t whole into mu n into delta t plus order of delta t plus P n plus 1 t into 1 minus lambda n plus 1 delta t minus order of delta t whole into mu n plus 1 delta t plus order of delta t plus P n minus 1 t into lambda n minus 1 delta t plus order of delta t whole into 1 minus mu n minus 1 delta t minus order of delta t. And this expression can be simplified further. P n t into 1 minus lambda n plus mu n into delta t plus P n minus 1 t into lambda n minus 1 delta t plus P n plus 1 t into mu n plus 1 delta t plus order of delta t, where n is greater than 0, and P 0 t plus delta t equal to P 0 t into 1 minus lambda 0 delta t plus P 1 t into 1 minus lambda 0 delta t whole into mu 1 delta t plus order of delta t, which is equal to P 0 t into 1 minus lambda 0 delta t plus P 1 t into mu 1 delta t plus order of delta t when n equal to 0. Rearranging and dividing both sides by delta t and then taking limit as delta t tends to 0, we get d P n t dt equal to minus lambda n plus mu n whole into P n t plus lambda n minus 1 P n minus 1 t plus mu n plus 1 into P n plus 1 t, and d P 0 t dt equal to minus lambda 0 P 0 t plus mu 1 into P 1 t. In the steady state, we have P n dash t equal to 0 and P 0 dash t equal to 0. Therefore, substituting these values in the above equations, we get 0 is equal to minus lambda n plus mu n into P n plus lambda n minus 1 into P n minus 1 plus mu n minus 1 into P n plus 1, where n is greater than 0, and 0 is equal to minus lambda 0 P 0 plus mu 1 into P 1 for n equal to 0. These equations constitute the system of steady state difference equation for this model. Now, we would like to solve these steady state difference equations, and we have P 1 equal to lambda 0 by mu 1 into P 0, P 2 equal to lambda 1 by mu 2 into P 1. Putting the values of P 1, we get P 2 equal to lambda 0 lambda 1 by mu 1 mu 2 into P 0. Similarly, we get P 3 is equal to lambda 0 into lambda 1 into lambda 2 divided by mu 1 mu 2 mu 3 whole into P 0. And proceeding in this way, we get P n is equal to lambda 0 lambda 1 lambda 2 up to lambda n minus 1 divided by mu 1 mu 2 up to mu n whole into P 0 for n greater than equal to 1. Now, since summation n equal to 0 to infinity P n equal to 1, we have P 0 plus P 1 plus P 2 plus dot dot dot, which is equal to 1, and if we put the values of P 0, P 1, P 2 etc., then we can find the value of P 0 as P 0 equal to 1 by S, where S is the sum of the series 1 plus lambda 0 by mu 1 plus lambda 0 lambda 1 by mu 1 mu 2 plus dot dot dot. Now, we will consider some particular cases. Case 1, suppose that lambda n equal to lambda and mu n equal to mu, that is the arrival rate and service rates both are constant. In this case, the series S becomes S equal to 1 plus lambda by mu plus lambda by mu whole square plus dot dot dot, which is equal to 1 by 1 minus lambda by mu. Then we have P 0 equal to 1 by S, which is equal to 1 minus lambda by mu, and also we get P n is equal to lambda by mu whole to the power n into 1 minus lambda by mu, which are the results already obtained in model 1. Case 2, here we consider lambda n as lambda by n plus 1 and mu n equal to mu, that is constant. In this case, the arrival rate depends on n inversely and the rate of service is independent of n. That is why this case is called the queue with discouragement, and the series S becomes S equal to 1 plus lambda by mu plus lambda square by 2 mu square plus lambda cube by 2 into 3 into mu cube plus dot dot dot, and which actually gives e to the power rho, where rho is equal to lambda by mu. Then we have P 0 equal to 1 by S, which is equal to e to the power minus rho, P 1 is equal to lambda by mu into P 0, which is equal to rho into e to the power minus rho, and similarly we can get P 2, P 3 and so on, and finally P n is equal to lambda to the power n by factorial n into mu to the power n into P 0, and which is equal to e to the power minus rho to the power n by factorial n for n equal to 0, 1 to infinity. Here we observe that Pn follows Poisson distribution, where lambda by mu equal to rho a constant. The value of rho may be greater than 1 or less than 1, but it should be finite. Case 3, we suppose that lambda n equal to lambda and mu n equal to n mu, and mu n equal to n mu indicates the infinite number of service stations. In this case, the arrival rate is independent of n, but the service rate mu n increases as n increases. Here we assume that there are infinite number of service stations. The word infinite means that the service stations are available for each arrival, but it does not mean that all the infinite service stations will remain busy every time. It actually means if n customers arrive, then n service stations will be available for all n equal to 0, 1 to infinity. Obviously, no queue will be formed in this case, because each arrival will immediately enter the service facility. In this case, the series S becomes S equal to 1 plus lambda by mu plus lambda square by 2 mu square plus lambda cube by 2 into 3 into mu cube plus infinity, which is equal to e to the power rho. Then we have P 0 equal to e to the power minus rho, and P n is equal to e to the power minus rho into rho to the power n by factorial n, which is again the Poisson's distribution, which again it represents the Poisson distribution. Now, let us take an example and see how the results of this model can be applied to solve some keying problem. Suppose that problems arrive at a computer center in a Poisson fashion at an average rate of 5 per day. The rules of computing center are that any man waiting to get his problem solved must aid the man whose problem is being solved. If the time to solve a problem with one man has an exponential distribution with mean time of 1/3 day, and if the average solving time is inversely proportional to the number of people working on the problem, then to find the expected time in the center for person entering the queue. Here we have the arrival rate lambda equal to 5 problems per day, service rate mu equal to 3 problems per day. Then the expected number of persons working at any specified instant is Ls equal to summation n equal to 0 to infinity n p n, where p n is equal to 1 by factorial n into lambda by mu whole to the power n into e to the power minus lambda by mu. The expression for phi n is already obtained before. So, using this expression for phi n and simplifying, we get Ls is equal to lambda by mu, and putting the value of lambda and mu, we get Ls equal to 5 by 3 persons. Now, the average solving time, which is inversely proportional to the number of people working on the problem, is 1 by 5 day per problem. Therefore, the expected time for a person entering the queue is 1 by 5 into Ls days. Putting the value of Ls and converting into hours, we get the expected time for a person entering the line is 8 hours. Let us take another example. A shipping company has a single unloading berth with ships arriving in Poisson fashion at an average rate of 3 per day. The unloading time distribution for a ship with the unloading cruise is found to be exponential with average unloading time half day. The company has a large labor supply without regular working hours, and to avoid long waiting lines, the company has a policy of using as many unloading crews as there are ships waiting in line or being unloaded. We have to find the average number of unloading crews working at any time and the probability that more than 4 crews will be needed. Here the arrival rate lambda equal to 3 ships per day and the service rate mu equal to 2 ships per day. Therefore, the average number of unloading crews working at any specified instant is Ls, which is equal to summation n equal to 0 to infinity n p n, and which gives lambda by mu, which is equal to 3 by 2 crews. The probability that more than 4 crews will be needed in the same as probability that there are at least 5 ships in the system at any specified time. Therefore, we can write summation n equal to 5 to infinity phi n, which is equal to summation n equal to 0 to infinity p n minus summation n equal to 0 to 4 phi n, and using the expression for phi n and simplifying, we get this as 0.019. We were discussing model 1 general, which is MM1 infinitive FCFS. This model is general in the sense that the arrival rate and service rate are assumed to be dependent on the size of the system. However, this model has a limitation. In this model, we have assumed infinite capacity of the system, which may not be applicable in practice. So, now we are proceeding to develop another model, which is model 2, where we consider finite capacity of the system. Let us start our discussion on model 2, which is MM1 N FCFS. This model is based on all assumptions of model 1 except a limit on the capacity of the system. Here we consider the capacity of the system as capital N. This implies that once the queue reaches its maximum length of capital N customers, no additional customers will be allowed to enter into the system. Therefore, the difference equation of model 1 are valid for this model as long as n is less than capital N. The additional difference equation for n equal to capital N is as shown in the slide. The corresponding differential difference equation can be obtained as dpnt dt equal to minus mu p capital N t plus lambda p capital N minus 1 t, from which the resultant steady state difference equation can be obtained as minus mu p capital N plus lambda P capital N minus 1 equal to 0, and therefore, we get the complete set of steady state difference equation for this model as mu P 1 equal to lambda into P 0 for n equal to 0, mu P n plus 1 equal to lambda plus mu whole into P n minus lambda into P n minus 1, where 1 less than equal to n less than equal to capital N minus 1, and for n equal to capital N, mu P capital N is equal to lambda P capital N minus 1. In this case, the service rate mu should not exceed the arrival rate lambda in order to obtain the steady state conditions. From the first two difference equations, the probability of n customers in the system where n can take the value 0, 1 to up to capital N minus 1, the probability can be obtained as P n equal to lambda by mu whole to the power n into P 0, where n is less than equal to capital N minus 1. Also, we see that for this value of P n, the third difference equation holds for n equal to capital N, and therefore, we can write P n equal to lambda by mu whole to the power n into P 0 for n less than equal to capital N. In order to obtain the value of P 0, we can use the relation sigma n equal to 0 to capital N P n equal to 1, and this gives P 0 equal to 1 minus rho by 1 minus rho to the power capital N plus 1 when rho is not equal to 1, and P 0 equal to 1 by capital N plus 1 when rho equal to 1. Hence, we have P n equal to 1 minus rho divided by 1 minus rho to the power capital N plus 1 whole into rho to the power n, where rho is not equal to 1 and n lies between 0 and capital N, and P n equal to 1 by capital N plus 1 for rho equal to 1. It is to be noted that when capital N tends to infinity, the steady state solution P n would be equal to 1 minus rho into rho to the power n, and this result is the same as we obtained in model 1. We will now discuss some characteristics of this model. The average number of customers in the system is given by L s equal to summation n equal to 0 to capital N n P n, and if you put the value of P n and simplify it, then the value of L s can be obtained as shown in the slide. The average queue length is given by L q, which is equal to summation n equal to 1 to n minus 1 into P n, and which can again be written as L s minus summation n equal to 1 to capital N P n, and using the value of P n, the average queue length can be obtained as shown in the slide. Under general conditions of arrival, departure and service discipline, it can be proved that L s equal to lambda W s and L q equal to lambda W q, which are known as Little's formula. And then by definition, we have WQ equal to WS minus 1 by mu. WQ is the expected waiting time in queue and WS is the expected waiting time in the system. So, expected waiting time in the queue is equal to expected waiting time in the system minus service time. And now, multiplying both sides by lambda and using the result above, we easily get LQ equal to LS minus lambda by mu, and thus we have WS equal to LS by lambda and WQ equal to LQ by lambda. Now, we will take an example. Consider a single server queuing system with Poisson input and exponential service time. Suppose that the mean arrival rate is 3 calling units per hour, the expected service time is 0.25 hour and the maximum permissible calling units in the system is 2. We have to derive the steady state probability distribution of the number of calling units in the system, and then we have to find the expected number in the system. This example is an application of module 2, which we have already discussed. And in this example, we are given that lambda equal to 3 units per hour, mu equal to 4 units per hour, and the capacity of the system capital N equal to 2. Then the traffic intensity rho is equal to lambda by mu, which is equal to 3 by 4. The steady state probability distribution of the number of n customers, which are actually the calling units in the system, is P n, which is equal to 1 minus rho into rho to the power n by 1 minus rho whole to the power capital N plus 1. Putting the values of rho and capital N, we get P n as 0.43 into 0.75 whole to the power n when rho is not equal to 1. And similarly, we find phi 0, which is equal to 1 minus rho by 1 minus rho to the power capital N plus 1, which is equal to 0.431. The expected number of calling units in the system is then given by Ls equal to summation n equal to 1 to capital N npn, and putting the values of Pn and simplifying, we get Ls equal to 0.81. Let us consider another example. Assume that the goods trains are coming in a year at the rate of 30 trains per day, and suppose that the inter-arrival times follow an exponential distribution. The service time for each train is assumed to be exponential with an average of 36 minutes. If the yard can admit 9 trains at a time, which is the capacity of the system, then we have to find the probability that the yard is empty and the average queue length. We are given that lambda is equal to 30 by 16 to 24, that is equal to 1 by 48 train per minute, the arrival rate converted into minute per minute, and mu is the service rate, which is equal to 1 by 16 train per minute. Therefore, traffic intensity rho is equal to lambda by mu, which is equal to 0.75. The probability that the yard is empty is given by P0, which is equal to 1 minus rho by 1 minus rho to the power capital N plus 1, and this gives P0 equal to 0.28. Similarly, we can calculate the average queue length LQ by using the expressions already derived. We find LQ is equal to 1.55. In this module, we have developed and studied two queuing models. Model 1 general, which is MM1 infinitive FCFS, and model 2, which is MM1 in FCFS. In the first model, the arrival rate and service rates are assumed to be dependent on the size of the system, whereas in the second model, the capacity of the system is assumed to be limited. In the second model, if the customers are coming to the system when the queue length is more than n, then there is no scope of entering into the queue. The interpretation of the model can be like this: there are only rooms which are available for capital N number of customers only, or the arriving customers which can go for their service elsewhere when the length of the queue is greater than or equal to n. With these comments, we end this module.